Greetings. Welcome to the 21st lesson in a series of lessons on basics of power systems engineering. Starting with this lesson, I'll be covering topics in the area of three-phase power systems. To lay down the background for our work, I will be covering the generic trio of balanced phasors in this lesson, and we'll use the results in the upcoming lessons on balanced three-phase power systems. If you're familiar with the topic, you can skip this lesson and move on to lesson 22 instead. Let's start with three phasors A, B, and C that are of equal length and have phase angles that are 120 degrees apart, each from the other two, as shown on the next slide. Clearly, I could have assigned the A, B, and C in another way, that is to say, in the opposite direction, calling this phasor to be B and this phasor to be C in this way. This arrangement is shown on the next slide. Besides the naming difference, the substantive difference between these two sets is that the set on the left, the phasor B lags phasor A, and phasor C lags phasor B, and phasor A lags phasor C, all by 120 degrees one from the other. While in the figure on the right, phasor B leads phasor A by 120 degrees, and C leads B by the same amount, and A leads C by the same amount. As a reminder, and by convention, counterclockwise rotations are considered positive, and clockwise rotations are considered to be negative in degrees. The trio of phasors on the left are said to be forming an ABC, or positive sequence set of phasors, while the trio on the right is called an ACB, or a negative sequence set of phasors. And they're written out on this slide: ABC, or positive sequence, and ACB, or negative sequence. Sum of three balanced phasors, whether positive or negative sequence, is always 0. It's easy to see this graphically. Let's form A plus B plus C. And let me first form B plus C by completing this parallelogram and connecting from O to the opposite side. We'll see that the sum of B plus C is actually equal negative A. So if I substitute here for B plus C, I substitute negative A, the result is going to be 0, A minus A. Here we see the algebraic relation between pairs of phasors in each set. B equals A with negative 120, C equals B with negative 120, and A equals C with negative 120. Those are for ABC set. For ACB set, we have similar equations, except that the angles are all positive 120. B leads A, C leads B, and A leads C. I wrote B in terms of A, C in terms of B, and A in terms of C in each case, but we can easily reverse that. If I want to find A in terms of B, I'll take the original equation, the one written on this page here, and I can multiply both sides by a 1 with positive 120. On the right hand side, the 120s add up to 0, so I'll have A. On the left hand side, I will have B with plus 120. And if I reverse this, I'll have A in terms of B. A equals B with 120 degrees positive. That can be done for any of these and any of these, but it's easier to remember just one set of three equations for each. And if we needed A in terms of B, or B in terms of C, or C in terms of A, we can always reverse the sign, and that will give us the answer. I'll be focusing my attention for the rest of the lesson on positive sequence sets, because positive sequence systems are the ones most commonly encountered in power systems. The results of our discussions are applicable to the negative sequence sets as well, with small but important modifications, and I'll be pointing them out as they come up. So here is our set of three phasors that form a balanced positive sequence set, ABC. I'll be calculating the pairwise differences of these phasors. I'll explain in our next lesson, in working with three-phase voltages and currents, why the differences between pairs of phasors form an important quantity, and we'll apply the results directly from this lesson. With the three phasors ABC, we can form 6 different differences, and those are A minus B, B minus C, C minus A, or you can reverse that and each one of these and write them as B minus A, C minus B, and A minus C. Clearly, either half or either trio of equations can be obtained from the other by multiplying the other set by a negative. But let me calculate A minus B, B minus C, C minus A as our main focus, because they'll be most useful ones to have handy. And anytime you want any member of this other set, you can just multiply these members by a -1 to get that. So let's form A minus B. I'll substitute for B in this equation from here. So it becomes A minus A with -120. Let's factor out the A and rewrite this as A times this quantity, which is purely numerical, 1 minus 1 with -120. If you put these two numbers as in your calculator and subtract them, you'll get something like A times 1.73205, etc., with a positive 30 degrees angle. And I have it written out here. A minus B equals A times the square root of 3 with 30 degrees, because that's 1.73, what was it, 2501, etc., is the square root of 3. I can rearrange this to look like this. A minus B equals the square root of 3 times phasor A with 30 degrees angle added to the angle of A. And let me draw that here. So this phasor, A minus B, would have a 30-degree angle with the horizontal. And we'll have a length that is square root of 3 times absolute value of A, or magnitude of A. I have a better diagram for it on the next page. Here it is. A minus B, 30 degrees and leads phasor A by 30 degrees, and has a magnitude that's square root of 3 times magnitude of A. Because the relation between B and C is the same as relation between A and B, as they have the same magnitude and C lags B by 120 degrees, we won't really need to calculate B minus C. We know it's going to have this very shape with the letters rotated. So B minus C would be square root of 3 times B with 30 degrees. And similarly, well, let me show you the phasor diagram for it, which is shown on this slide. So B minus C would be this downward phasor. And C minus A will be given as the square root of 3 times C, phasor C with 30 degrees. And here is its phasor diagram. The takeaway is that in a positive sequence balanced three-phase set, subtracting any phasor X from another phasor Y to write them as Y minus X results in a phasor that has a magnitude that's square root of 3 times the magnitude of either phasor. Let's call it square root of 3 times Y, phasor Y, and is 30 degrees ahead of the phasor Y. So let me just write it as square root of 3 times Y with 30 degrees. These are phasors, and because I cannot write them in bold font, I'm just going to put a dash over them to emphasize that these are phasors from the positive sequence set of phasors. By the way, for a negative sequence set, the magnitude of the difference is still square root of 3 times magnitude of the ABC phasors. But the angle is negative 30 degrees in these equations. So if this were to be a negative sequence set, these 30s will turn into negative 30 degrees. Same here and same here. This is an important difference between the two systems. It may be instructive to see the relation between balanced phasors and their pairwise differences geometrically as well for those who like geometry and trig. I'll go over that quickly. Here's a positive sequence set of phasors. Let's form the difference A minus B graphically. But since I'm better familiar with addition of phasors than subtraction of phasors graphically, I'm going to form the negative of phasor B and then add phasor A to this negative. So if you rotate B 180 degrees, you'll get negative B. So instead of subtracting A minus B, I will be adding A plus the negative B phasor. And of course, addition is result of, graphically, is a result of completing a parallelogram over the two sides and then drawing the diagonal. If you're familiar with vectors and vector operations, you'll have a good appreciation of the operations with phasors because they are very similar. Here is the phasor negative B, and again completing the parallelogram, we can find the sum of A and negative B graphically, and here it is. Let's find the phase angle and magnitude of this A minus B. First, notice that this parallelogram that was constructed over A and negative B is actually a rhombus, a special case of a parallelogram, because all four sides are equal in length. What that means is that these two triangles this one, and this one are congruent due to side-side-side equality of the sides, which means that these two angles are congruent to each other. This whole angle is 180 minus 120, which is 60, so half of it is 30. This angle here is 30 degrees. So that establishes the fact that A minus B leads A by 30 degrees, as you can see in this diagram. Now let's find the length of the A minus B. To do that, let me draw a altitude of this triangle. Because this is an isosceles triangle, the altitude bisects the base. Let me find the length of half of that base. We know this is a 30-degree angle, so this length, the half length, would be magnitude of A, or length of OA, times cosine of 30 degrees, which is to say magnitude of A times square root of 3 over 2. To get the length of A minus B, we need to double this, which results into square root of 3 times magnitude of A. Let me change the color of the phasor A minus B to have it stand out better. The two other differences are formed in the same way, resulting in the same diagram as was seen earlier for the phasor differences for the positive sequence set. And here is the completed diagram. This diagram shows that not only the sum of A plus B plus C is 0 in a balanced set, but that also the sum of the differences is 0, which is seen both graphically as well as with a simple expression. Graphically, we see that they are balanced. The A minus B, B minus C, and C minus A form a positive sequence set of balanced phasors. The angles between them are 120 degrees, and so they do add up to 0. But with equations, we have A minus B plus B minus C plus C minus A, and clearly they all cancel each other out. A and A, negative A, B and negative B, C and negative C. Or you can look at it as A plus B plus C minus A plus B plus C. Well, we know that each of these sums are 0. So the total is 0. You may sometimes see the difference phasors arranged on the phasor diagram in a different way, as shown on the next slide. Here, each difference phasor has been translated to a new position. As with vectors, translating phasors on the plane does not change their value. As I had mentioned earlier, for a set of ACB or negative sequence phasors, the phase angles would be negative 30 in the equations that relate the differences with the individual phasors. Next slide shows a diagram of the negative sequence set along with those difference equations. Here they are. I'll have the positive sequence set side by side for comparison. On the left you have ABC or positive sequence set of phasors, and on the left. On the right you have the ACB or negative sequence set of phasors. Notice that in ABC or positive sequence, each difference is 30 degrees ahead, or leads by 30 degrees the initial vector, the initial phasor in the difference. So this one is 30 degrees, leads A by 30 degrees. This one leads C by 30 degrees. And this last one, B minus C, leads B by 30 degrees. Whereas for the negative sequence set, A minus B lags A by 30 degrees because of the clockwise direction. And B minus C lags B by 30 degrees. And C minus A lags C by 30 degrees. It might be worthwhile to commit to memory the equations on this page, in particular the set on the left for the positive sequence sets, because they'll pop up throughout analysis of three-phase power systems. Next lesson, we will move the discussion for generic phasors from generic phasors to voltage and current phasors in three-phase systems. We are now at the end of lesson 21. My name is Fouad Albandi. I am a PE in electrical power engineering. You find my name, web address, and email address on this slide. My web address is own-your-destiny.mylearnworlds.com. My email address is the same as this part of the web address, except the hyphens are spelled out. own-your-destiny@yahoo.com. I invite you to visit my website for comprehensive modules on power systems engineering. If you like my presentations, please be sure to click subscribe button and the notification bell. Thank you for watching this video, and I hope to see you soon in another one of my presentations.